Hi, my name is Amy Sullivan, and I'm the current president of AAAR. It's my pleasure to welcome you to our 38th in our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, the editors of AS&T select a high-impact journal article to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us a chance to all gather outside of the annual conference. In addition, these lectures are being recorded and will be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, each of these lectures is being hosted by one of our student chapters. I want to thank all of you for joining us and for everyone who's helped to make these lectures happen. And with that, I'll turn it over to our student chapter from Clarkson University to get us started. Thanks.
Thank you, Amy. Hello, everyone. Welcome to another exciting lecture in the AAAR lecture series. I'm Nagarajan Radhakrishnan, the current president of the student chapter here at Clarkson University. And it's my great honor to introduce today's speaker, Professor Sotiris E. Pratsinis. Professor Pratsinis is an emeritus professor of process engineering and material science at ETH Zurich. He received his master's and PhD from UCLA. Over his remarkable career, he has authored more than 400 peer-reviewed publications, holds over 20 patents, many licensed to industries, and has trained a generation of scientists who now hold leadership positions in academia and industry worldwide. Among his many achievements, he led the development of the first nanoparticle production facility at an academic institution with a capacity of producing particles at the rate of kilograms per hour, a world record that still stands today. He pioneered flame spray pyrolysis techniques, now widely used for nanoparticle synthesis in both research and industry. He also contributed decisively to environmental policy by identifying the origins of nanosilver toxicity and developing processes for curing it. Today, we have the privilege of hearing him present the work, A New Mean-Free Path for Air and Its Impact on Diffusion of Tiny Aerosol Nanoparticles. The lecture will follow the usual format with around 45 minutes of presentation, followed by questions and discussion at the end. So let's all join together in welcoming today's speaker, Professor Pratsinis. The virtual floor is yours.
Thank you, Naga and Amy, for giving me the opportunity to present some of the work of my associates. Typically, I have them to present it, but because of the topic has such a broad impact in the aerosol society, they asked me to give this presentation, but nevertheless, Dimitris Tsalikis, the person who is behind all of this work, is standing by to really articulate the details. So what I will give you here, let me paraphrase St. Paul on his second letter to Corinthians, that I will give you a fragrance of knowledge about the new mean-free path and its impact, this time on diffusivity of tiny aerosol nanoparticles. During the presentation, I will mention some spin-offs, but I need to make a statement here that I have no shares or board position in companies, especially those that come from my laboratory. So whatever I say, it's really my own opinion, and I have not an agenda behind it. So let's get started. What we do here. The focus of our research program in Zurich is in aerosol synthesis of materials. In one sentence, we try to understand how aerosol particle characteristics affect material performance. And this, I cannot emphasize how important is the attention to detail here. I can give you an anecdote. About 30 years ago, when I was giving a presentation at DuPont, people, they asked me how accurately you can calculate the particles, how accurately you can measure the particles. At that time, the big thing was the aerosol, the EAA, the electrical aerosol analyzer. I told them particle sizes in the order of about 30%. They told me, this is not acceptable. Maybe your instruments, they will not detect the particle size difference, but our accountants, they will. Why? Because we make so much, and a slight difference on the correct particle size has an immediate impact on the product that they sell. So let me give you an example here. Let's talk about titanium dioxide. For this material, if it is about 200 nanometers, is the dream white pigment, especially in the rutile phase. If, however, it is in this ramified structure that you see to my right here, and is an anatase, then it is best for photocatalysis. So in our laboratory, we focus on the fundamentals, and essentially the lecture today is on the fundamentals, but we always have in our eye for applications, and most notably in catalysis, biomaterials, sensors are some of the areas where our students have making some major impact in the corresponding fields. For example, our claim to fame, as Naga mentioned, is this flame spray pyrolysis, essentially combustion of solutions that they can make an array of particles. Today, the record, a new paper by Mark Suichert came out and actually showed that you can put together 22 different cations for these high entropy materials. A company from our laboratory, Partech, with Dr. Wegner, that you see here at the bottom, now has sold this device in 63 industrial and academic laboratories worldwide, pursuing different applications. Let me mention the latest one, which is another spin-off, which is actually making highly selective gas sensors for detection of adulterate liquor. Really a major problem in the developing world. So what you see here at the device, this is an aerosol-made sensor that is preceded by an absorption column, and from there you are taking a vapor from a liquor, a whiskey, for example, and then you go through this and device from the absorption column and then the sensor, and actually on the iPhone you can see the methanol level as well as the ethanol. That way you can calibrate even on the site the ethanol level and detect how much methanol exists. This looks like that now, the commercial device. This is the whole device here, and you see it here used inside distillation factory for making liquor. And this now company, since 2022, has sold its gadgets in 35 countries in 6 continents. And here is the chief technical officer, a former student of mine. And actually, they are really doing very well. And for many aspects, not only the applications, as you saw here, for the distillation factory, but also in other aspects in the medical fields, because it's very important to understand the difference of methanol intoxication versus ethanol. Ethanol intoxication, usually you clean it up, the stomach, and you're okay. But for methanol intoxication, you need to clean up the blood because it's completely different. So having a device that very quickly can detect the type of intoxication can be sometimes a life-saving issue. Having said this, I hope you can understand now what we're looking for, because properties of tiny particles are very important. And actually, we start in this field, which is the topic of today, trying to develop from first principles what we call these fractal laws. And then we encounter, when we try to validate the basic kinetic theory that dictates that gas molecules are actually colliding like billiard balls, the so-called elastic collisions. And then, as in every aerosol textbook, you have this drawing, the molecular trajectories after its collision with another molecule. And the average distance of those is the mean free path that everybody in this audience knows. However, gas molecules, especially air, which is very important for environmental applications, is diatomic, okay? So, and not only that, also has finite force fields around them. So what we did here, we say, okay, let's use the standard description of this force field, which is nothing else but Lennard-Jones potentials, as you can see here, the potential energy versus the separation distance, and then looking intramolecular, the so-called spring model. And with this now, let's look at the air by fully atomistic simulations for both oxygen and nitrogen, and look at 2 distinct cases. The first one, in these limiting cases, we will call it the hard sphere. We'll assume that the molecules are truly perfect spheres, which is this. In that case, our simulations have to match whatever is out there, the kinetic theory in specific. in a second special case, we will assume the molecules to be perfect spheres, but with a force field. And this will contrast against the complete picture, the true picture, which is that of the fully atomistic model of a diatomic structure and the finite force field around its molecule. So if we look into this system here and look, first, you see what you know very well, that gas molecules collide like billiard balls, perfect elastic collisions. This is what we call the hard sphere model, the abbreviated HS model. Now let's look at the second limiting or reduced case with the Lennard-Jones model, and then you can see now that the same thing happens. However, the collision is soft, as you can see here, very gentle softness here. And now at the point of collisions here, we do not have this classic elastic collision where the angle of arrival is equal with the angle of departure. And now let's look at the real thing, the fully atomistic model. And now you can see the model that in the molecules in their diatomic structure collide these soft collisions. And again, the collisions are not elastic, is this so-called diffuse type or inelastic collisions. So you may, if you look at this, you say, so what? The difference is not that big. Yes, to the naked eye, here the difference does not look that big if we look at a specific collision. However, this is responsible for the so-called multi-body collisions. For example, here you can see three molecules at room temperature. Actually, they do collide, something that is not predicted by the kinetic theory of gases. Now, this is important because if we look now how many of these collisions you can have here, in this table here, I can show you at a temperature of 100 Kelvin, the classic two-body collisions, it's only 89%. In other words, more than 10% are multi-body collisions. But even if we look into the standard room temperature, 1% of these collisions is more than two bodies, the multi-body collisions. And this is actually quite important if we look into higher pressures. For example, you can see here, if we look at the fraction of multi-body collisions at different pressures on the column here, the two-body, three-body, four and five-body, and so on, at 5 atmospheres, more than 5% of the molecular collisions are multi-body. So, but the most interesting result, so what I probably you can see here, we have a very strong temperature dependence and pressure for this type of collisions. What is, however, very interesting and rather unexpected with what we typically use in aerosol science is that actually gas molecules can exhibit so-called orbiting or spurious collision. And now let's take a look here at the second reduced case, because the hard sphere model, the first one, which is a kinetic theory, does not predict something like this. So if we look at this here, you can see now these two molecules coming because of the force field around them. You can have multiple collisions. And this actually, why? Because of the attraction and repulsion. Sometimes, depending on the momentum of the molecules they approach, it's not enough to allow them to walk. And actually, only at some point after another event, maybe a gas molecule even farther away, just affecting the force field, they can have this separation. And now how this looks into the real system when I have this so-called diatomic molecules and full rotation here. And you can see now they come, one atom collides with another atom of the other molecule, and again, and another again, and another, as you can see here, again, before they will separate, okay? And this results in this so-called orbiting or spurious collisions. And what I show you here, I show you that with the Lennard-Jones model, you get to the left here, these collisions, they multiple ones, and they take even within picoseconds, every one of those. Of course, this I will define it as a single collision event, okay? There are multiple collisions, but in terms of counting them, it's only one collision event. So this is what I show you with the fully atomistic model. But then the question is it really new? And here, I always remember my academic advisor, Sheldon Friedlander, who told me, when you have something which seems really new, there are two cases that they will happen. Either you are wrong, or someone else must have seen something like that before. So there is nothing truly, truly new, or very rarely something of that nature. So be careful. So to be honest with you, we sat on this work for a few years before we are ready to publish it. So, and what actually helped us is this picture from the textbook of molecular theory of gases and liquids by Hirschfelder, Curtis, and Baird. And for the chemical engineers in this audience, Byron Baird is the one who has written the Bible of chemical engineers, the transport phenomena. And what you see here, they have drawn actually these forefathers, how molecules should collide. They talked here, as you can see, grazing collisions. They talked about head-on collisions, which is nothing else than what we believe is happening today between gas molecules colliding this ballistically. But they even jotted down orbiting collisions. You can see here at the artist, of course, beautiful, but the real thing, as you just saw with the simulations, is not these perfect orbits, but because of this rotation of the molecules and all of these collisions between different atoms within the same molecule, then you can have these more complicated patterns that you saw before. So with this, we went ahead and by looking into the spurious collisions in the paper that we published last year in the Aerosol Science Technology, we wanted to see again what is the effect of temperature and pressure on those. And what I have here on the ordinate, I have this the fraction of the spurious collisions. And I remember here, I'm talking about every spurious collision here. It's not the 3, 5, 10 of, they are talking about spurious or orbiting collision events. Each one, even though they are 5, 10, or 20 even, we only count this as one. So let's look at the extreme case. For 100 degrees Kelvin, 65% of the collisions at 1 atmosphere, here this is actually spurious collisions. Now, as we go to more realistic systems here, the 300, you can see here that this is almost 40%. And if we look into this 1 atmosphere, it is actually very close. And if we increase the pressure, they don't change very much, although as the temperature increases, the fraction of collisions, of orbiting collisions, drops significantly from the 65% down to 15 at 3000 Kelvin. So what we learn from this is that there is a strong dependence on temperature, but practically pressure independent. Okay, and this comes, of course, for the sensitivity of the force field to temperature, as we know from the definition of the Lennard-Jones potential. So having said this, now let's see what it means in terms of what it matters, namely the number of collisions and practically the mean free path, which is of prime interest for an aerosol scientist. So here I have the collision density predicted by the 3 different models. First of all, we have to put what the kinetic theory predicts, the classic theory by Maxwell, and you can see here the bar, and the hard sphere model comes right on. Perfect agreement, validating, as a matter of fact, these calculations. However, if we look into the Lennard-Jones model, remember again, this is the model where we are assuming molecules to be spheres, but to have a finite force field around them, attractive and repulsive. And you can see you have a significant increase. And if we go and to the actual model where you have both the diatomic structure and the and the force field, you can see here that the number of collisions is almost 70% more than what the kinetic theory predicts. Why? Because of this increased interaction, the spheres of influence, if you like, the molecules have the opportunity to collide more frequently. And of course, this will have a direct impact on the mean free path. So by calculating now mean free paths by every molecule here, you can make these probability diagrams, and namely how many times the the free path of molecules as a function of essentially length here. And you can see, of course, that it decreases as the mean free path increases. And you see here, this is at different times, and 0.5 nanoseconds, 1 or 6. And you can see that eventually these curves converge. And from this now, by taking the arithmetic average of those, you can calculate the mean free path of air. And the kinetic theory gives this classic result at this 300 degree Kelvin and 1 atmosphere of 67.6 nanometers, while the hard sphere models is 70 plus minus 2, and the Lennard-Jones 42, and the fully atomistic 38.5. Clearly, the mean free path is almost half that of what is in every textbook today. And this is of significance for various reasons. But before I will get to the significance and to the second part of this presentation, let's see now how the mean free path is affected at different temperatures and pressures. Here I have plotted the mean free path for different temperatures. For example, with the blue circles that you can see here is the mean free path at the ambient temperature, 300 degree Kelvin. And you can see, of course, as the pressure increases, the mean free path decreases. And of course, as the temperature increases, the mean free path becomes longer, almost like for, you can have at 1 atmosphere here, the mean free path to be in the order of hundreds. And of course, this is important in combustion, for example, mean free paths can be in the order of hundreds of nanometers, which is very important because aerosol formation in combustion actually largely takes place in the free molecular regime. And again, what is interesting here that if we look how these data scale with pressure, they go exactly inversely proportional to pressure. Perfect. This is consistent with the kinetic theory of gases. However, if we look at the other way around, how does the mean free path at different temperatures for fixed pressures, a half an atmosphere, 1, 3, or 5, you can see again, as you would expect, as the pressure goes down, the mean free path goes up, as you saw on the previous graph here, more or less. And again, here, if we go to see what power of temperature scales them up, you see now that here, the power is not T, as we had it plainly before, but now to the 1 to the 0.23 of the power law. So with this, now we can propose a new equation for mean free path for air, what you see here with this pressure and temperature dependence. And now how we can juxtapose this, what is already in the textbooks. Typically, if you open the textbooks, let's say Freelander or Seinfeld or Heinz, the mean free path is given by this equation, which is credited to Jenkins. And of course, you recognize here viscosity of the air, density, pressure, and there is always a factor, a U here, which is this 7-digit number, very important. And this is actually what has been proposed and matches very well the kinetic theory of gases. However, with these calculations, the new mean free path, we can actually use exactly the same simplified formula, but the U has to be what you see here in red. This is the new value. And you can see here the surface of the mean free path as a function of pressure and the viscosity, which is the easiest way to actually calculate it when you don't have data very easily accessible to it. So now the question is, so what? A new mean free path. Of course, common sense will tell you the continuum now regime is actually reaching smaller sizes than what it is thought until now. Another very important, and probably I believe the most important result, is subcritical cluster nucleation dynamics. We have been looking with Dr. Tsalikis here into this, and actually we've been very much impressed that hardly people account for the collisions of clusters with the surrounding molecules. And this is important because now molecules and clusters can be of equivalent size action. Maybe another important is diffusivity, and this is what we will talk to give you an example how the new mean free path impacts the diffusivity of nanoparticles. And of course, as you will expect, nanoparticle coagulation is affected, especially in the free molecular regime. So with this, let's focus on the diffusivity as we promised on the title of this webinar. And let's see the state of the art of diffusivity of aerosol nanoparticles. If you open every textbook, this is the standard picture that you have. You have the diffusion coefficient as a function of the particle diameter. For very large particles, micrometer and above, it is the classic Stokes-Einstein equation. For very, very small particles, this is the Epstein. And the one that Epstein equation, which you can see it here, with to be 90% to be the so diffuse collisions and of particles and gas molecules, and 10% roughly specular or ballistic collisions. And then in between, you have the Stokes-Cunningham-Millikan equation, or Stokes-Cunningham, as it is in most textbooks, which is now even in the ISO. And you see here with the blue, the different constants of this interpolation between the two regimes, the continuum and the free molecule and the Epstein. And this, in particular, however, the focus of this is in the very tiny nanoparticles, on this very small, in the order of about less than 5 nanometers, because there is a significant debate in the literature. Since mid-80s, people, they have recognized that this Epstein equation or the Stokes-Cunningham, the interpolation, they don't match experimental measurements. First was people in Germany, they have recognized experimentally, and actually people proposed some theories, as I will describe it in the next few minutes. Very recently, a beautiful review was written by Professor Francisco Carbone and Lariba Andaluz, and they recognized and even mentioned that the Stokes-Cunningham-Millikan equation has a wide margin for improvements. And they are referring actually to this very tiny size regime. However, even on this beautiful review, look at the drawings. This is like a particle, a perfectly sphere particle. And you can see here, they very smartly, they have point out the force field around the particle, or here they have an agglomerate, and then they have around them the actual force fields. However, look at the drawing of the gas molecules, billiard balls. They don't recognize that, hey, even the gas molecules has a force field, and this may have an effect on the collisions between the particles, as you will see in the next few slides. So that's actually the topic of the lecture today. So why should we care about the 0.5 to 5 nanometers? Of course, beyond the basic science, for materials synthesis, where I have been working for a significant part of my career, this is, a paper by Buffet and Borel from our sister university in Lausanne, and showing the melting point of gold as a function of the particle diameter. This is a paper highly cited, more than 3,000 citations. And you can see here, up to about 50 angstroms or 5 nanometer, you see the melting point barely drops about 10%. However, if we go beyond 5, then we see this precipitous drop of the melting point, maybe 500 degrees, almost more than half of the value of the melting point. And this is actually what has excited people about 30 years ago to even talk nanotechnology or nanomaterials as the fourth state of matter. Nevertheless, this hype, as always, with something new in science comes up with it. We know that it is the most dramatic change for material properties, but also it's critical for diffusion, nucleation, as we just mentioned, and the free molecular coagulation. So what we did here with two fabulous colleagues, Dr. Karadima and Dr. Tsalikis, who is actually in the audience, and they will be happy to answer your questions about all of this work here. We took some characteristic particles, some well-defined nanoparticles, very small ones. In this case, fullerenes, as you can see here, from 0.4 nanometers, 0.7, 3, or 7 nanometers, and some amorphous silica nanoparticles, 0.7 to 3 nanometers. And you can see here the drawings for this, how they look like. So, of course, we will consider the nitrogen and the oxygen diatomic with this Lennard-Jones force field that we described to you already. So what we observed when we carried out the simulations, these are the typical ones. We saw grazing collisions, we say head-on collisions, we say orbiting collisions. Let me alert you, of course, that this tend to be, all of them actually, rather diffuse, hardly any specular, as we discussed. It also has been pointed out by Epstein and other colleagues, Fernandez de la Mora, Freelander, and so on. But now, let's take a look how particles diffuse in this environment of gas molecules. You can see here, this is a 1.5 nanometers silica molecule. And now I have these multicolored dumbbells. All of them are diatomic oxygen and nitrogen molecules. And I have them with different colors only to help you point out how the trajectories of the gas molecules form, because they go awfully fast. So if they have the same color, you will be confused. So this is an artificial only for convenience. So let me give you a flavor of how this takes place. And you can see now we have the classic rotation of the nanoparticle, and then you can see these molecules attacking it left and right. And for example, here you can see that you can even take a break and see how they come and then how they continue to, start from the beginning, but nevertheless, it's very fast. So we have this continuous collisions between gas molecules and particles, and these, of course, affect the trajectory of the particles, as you would expect. And when we put all of this down, and I will show you a few moments on the next slide, but at least you saw how everything moves, because from this movement of the particle, we will be able to do the mean square displacement calculation, and from that to extract the diffusivity. And now with the y trajectory, we have the center of mass of the particle, which is this property is what will be used to extract the diffusivity. But at the same time, we follow the movement of a surface molecule or a surface atom on top of the particle to see this rotation motion. And this is the black line that you see over here. Now, let me take a few moments here that can be of interest. For example, at some point you saw so typically we have multibody collisions with particles and gases is the standard. So I take a snapshot of these two green gas molecules, they collide at the same time. You can also have some repetitive, what do I call, orbiting collisions, which gives you the feeling that the gas molecule has been even absorbed onto the particle, because it is so close, as you see here, with this blue and gas molecule on top of the silica particle here. So with this, we can actually clearly point out that nanoparticle diffusive motion is governed by inelastic collisions with gas molecules. So what we do here, we take now, calculate, taking different trajectories like that, and we calculate here, we depict the mean square displacement as a function of time, and taking the average of those, and then we fit that with the classic MSD equation, and from that we get the diffusivity. Okay, that's the standard procedure how you get diffusion coefficients even in experimental systems. So with this now, let's see how these molecular dynamic obtained diffusivities compare with the predictions of the Stokes-Cunningham Millikan equation and Epstein, as you can see here. The line that you see here is the diffusion coefficient as a function of particle diameter, and I have only plotted the data up to 10 nanometers because this is the regime that it really matters. And here, if we put the calculations of these different particles that we generated here, we see here that for rather big nanoparticles, big now, it's a little bit of baby misnomer, but because we're talking about 4 or 5 nanometers, and you can see at 4 or 5 nanometers here, they match very well the Stokes-Cunningham and the Epstein equation, which gives us a confidence that for very big nanoparticles, they match what we know already. But what is interesting, regardless if it is silica or fullerene, you can see they have a steady deviation from the Epstein Stokes-Cunningham. And actually, if you go to the smaller and smaller particle sizes, the deviation can be almost an order of magnitude. Okay, so this is a significant result. And however, it cries also to compare with what is out there besides, particle dynamics. Because remember, these are molecules, the fullerenes, especially what we have here, these 20 carbon atoms, which is the smallest one, the 0.4 nanometer here. Amazingly well, this data match the experimentally based diffusivity equation for organics by Fuller, Schetter, and Giddings. This is an equation since 1966, primarily developed for hydrocarbon data, and especially in this regime is actually they have been developed with data up to about 0.8 nanometers or 8 angstroms. And this is in excellent agreement with the classic Chapman-Enskog equation here. The beautiful result here is that actually this equation is not only valid for its regime, and again, I will quote my advisor, Sheldon Freelander. They told me a good theory is valid even beyond its strict range of validity. But of course, this beauty stops at about 2 to 3 nanometers, as you can see here, because the 5 or 6, they no longer, it's too far away from its area of success. So with this, the question is, wait a minute, other people have looked into that. Where is our work stand against this? Beautiful work 20 years ago by Fernandez de la Mora and as Schmidt taught, they put a beautiful equation here, and our data match very well. They are right on their equation, which of course is limited for particles bigger than 2 nanometers. Another great, and this succeeds primarily due to the consideration of gas molecule diameter and mostly inelastic collisions, as we saw also with our movie. Another group of people, Professor Wang from Stanford University and his student Lee, they have developed another equation here, and you can see again, our molecular dynamics diffusivity data are right on their data as well. Of course, they stopped at about 1 nanometer. You may wonder now why they stopped and didn't go further than that. Well, all of them they do because Professor Tammet, who was the first one to propose a model for this regime, pointed out that there is a transition from the elastic gas molecules to inelastic particle gas collisions between 1 and 2 nanometers. Professor de la Mora was more conservative, stopped at 2. Professor Hai Wang was a little bit more bold, went all the way to 1, but both of them, they stopped because of that. What is, in other words, the vision that people believe that gas molecules collide elastically. So although they know, they have seen that particles and gas molecules are inelastic, and they expect at some point there will be a magic transition from this mostly 90% plus inelastic collisions to go 100% elastic. Of course, as you saw from our simulations, this is not true, where there are inelastic collisions dominate both the gas and especially diatomic gases here and particles. So with this, what we have here is, I will quote Don Eigler from IBM Al Maden Center in 1989, when this is the guy who made the IBM symbol by moving atoms of xenon to write by microscopy that by scanning thallium microscopy the symbol of IBM. And really, this is where we are with respect to tiny aerosol nanoparticle formation and manufacturing, because I didn't tell you this, but it is very difficult to make in the gas phase these very small nanoparticles and mass, as we have been doing this kilo per hour that Naga mentioned as he introduced me in this presentation. So with this, my time is up. So I have to come to the conclusions and actually point out that air molecules undergo largely diffuse non-specular collisions, that they are multi-body grazing and orbital ones with a mean free path about half that written in nearly all textbooks at ambient conditions. Regardless of size, aerosol nanoparticles experience largely inelastic collisions with gas molecules. And largely we speak above the 90% of Epstein, Freelander, or Fernandez de la Mora. And third, what you saw here with these diffusivity calculations of nanoparticles smaller than 5 nanometers, we have up to about an order of magnitude lower diffusivities than those by the Epstein and Stokes-Cunningham equations, even though they converge nicely for bigger particles, 4 to 5 nanometers to those. So what is the take-home message? Below 2 or 3 nanometers, be careful. Don't necessarily, especially if you're working on these very low DMAs, where for very small particles and clusters, maybe the numbers need to be corrected in that regime. Thank you very much for your attention, and I'll be happy to answer questions myself and Dr. Dimitris Tsalikis on this presentation or on the paper itself that the ASNT and the AAR selected for the presentation. Thank you.
Thank you very much, Dr. Pratsinis and Tsalikis, for this fantastic work and an insightful lecture. Yeah, as Professor mentioned, we have some time for questions. Feel free to type in the chat or unmute yourself and shoot your questions.
I saw one from Evangelos Stefanidis, or maybe not. The hand went down.
Hello, Dan Murphy. I have a question with the grazing collisions. Since these potentials don't ever go to zero, how do you set a threshold for what you call a grazing collision?
Maybe Dimitris can give an answer to that. If Dimitri, if you are not ready, I can do it, but it's about time for you to get the mic.
Yes, sure. I hope you can clearly hear me. Okay.
Yes.
Yes. So, like typically a grazing collision is just, I mean, for the audience who's not familiar, for anybody who's not familiar, it's just the deflection of a gas molecule from its original direction while it moves. Okay, if it experiences no forces, then it moves ballistically towards the direction. So it feels these attractive forces by the nanoparticle. These try to make a collision, try to bring the nanoparticle and the gas molecule together. But however, it moves fast, so it manages to escape. So that's what you don't see it a typical collision in the sense of these being very close together. It's a deflection from its original trajectory. Now, concerning your second question, is that we assume that above a certain threshold, which is about 12 angstroms, the intermolecular potentials are typically zero. So there's no interaction above this distance. So so from that distance and on, if it manages to escape, I mean, and it does not return back to make a collision, it means that the grazing collision has stopped.
If I can add here, it is very similar to the definition of the particle mean free path. When it changes direction, it is the definition of how we define the distance of the mean free path for particles, not gases. Dr. Nisner, the audience, you cannot hear you. Turn on.
Okay. Now I'm on the mic. Okay.
Perfect.
You should hear me, Sotiris.
Yes.
So it's a simple question I have. I mean, on the x-axis, you depicted simply the particle diameter, and the diffusivity is a property of the particle diameter, and you have shown the deviation according to your models. I mean, couldn't it be that the particle size is changing? I mean, like we have a diffusion diameter, an aerodynamic diameter. So I have more the feeling that the simple property, how to determine the size, seems to become different the smaller the particles become. So
yes, very good question. Very good question. First of all, for the fullerenes, you can see they have a very well-defined shape. We don't have to argue about the shape and the diameter. Now, because we are in this pre-molecular regime, the shape, it doesn't matter that much, okay? Because here you have the more or less collisions that there is no medium like with the aerodynamic diameter that we are talking about. So we're only looking at the displacement of this, and that's how we extract the diffusivity. And what we have used here is, as a matter of size, is the equivalent spherical size of this. Even let's look at this molecule that is here, or particle, I mean now this nanoparticle of about 1.2 nanometer. This is the equivalent spherical size of that one.
Yes, but with increasing diameter, they will have different specific weights. They have completely different internal structure. So the outer diameter and so might be the same, but not the internal structure. So I would expect a difference if there is a collision.
Very good question. Now let's look at this at the slide of at the 1.4 nanometer. This one, which are, you see, two different shapes here. This is to the left is the fullerene, and this is the silica. Yeah. They come right on. Same thing. I have the picture here for silica, but not for the fullerene. But you can imagine, as I saw in the beginning, it's a very compact structure. So these two are matching better. Now, if I had here a needle, maybe it's another extreme story, but we try to keep it here, the shapes, more or less compact to avoid issues like this.
Yeah, well, but if you would measure your particles by, let's say, diffusion battery, so there would be always the same base for determining the size, then I would believe that.
Okay, but if we go, let's go back to the actual calculation. Look at this mess. Okay, this is the v-square displacement. You have here a huge spread. But if you take enough of these trajectories, then you get the number that I put up on the ordinate of that figure. You understand? There will be variation, make no mistake. But by putting too many of those, we are able, with the statistics, to bring it to where it should be, we believe. And the matching on the bigger particle size, the 5, the 7, all of those tells us that this is not an incorrect approach.
Okay, we have to think about that. Thank you.
Thank you for your questions.
We do have a few questions in the chat. One question is, the modeling here was performed considering neutral diatomic molecules. Has the consideration been given to additional gaseous components, including water vapor and charged ions?
Dimitri, you want to take this?
The answer is clearly not yet. For the time being, we are working on. We have been working primarily on neutral gases, but we are quite on the work to move to include also water vapor. I mean, for other works, but primarily all this work has been implemented for neutral diatomic molecules.
We do have another question. How sensitive are the results to the threshold of 1.2 angstroms at which you assume the force goes to 0? I meant to say, it's 12 angstroms.
Dimitri, I think
yes.
Okay, they ask.
Actually, yes, they're absolutely right. Actually, it's not quite. They are perfectly insensitive. So, I mean, we performed when we calculated these results, when we carried out these simulations, we were always concerned because we measured, free path, which is 43% smaller than what we know. So we were very, very, very curious, about that, and we worked with extremely focusing on detail, and we carried out not just these typical calculation. If there is an impact, for example, concerning just the cutoff of the potential energy, but we used also different force fields, different ways to treat the intramolecular interactions, and the force fields have completely different parameterization schemes, and they all converged to the results shown concerning the free path of air. So if you have a force field that predicts the correct macroscopic behavior of the gas, so then you are confident that you are doing the work correct, and you should calculate the correct macroscopic behavior. So we utilized several force fields, different approaches to treat the intramolecular interactions, and as the force fields reproduce the correct air density, air viscosity, and air diffusivity, they all give exactly the same result. So it's purely insensitive.
Got it. Thank you. Another question. You've shown that the probability of particle-gas collision increases for nanoparticles smaller than 2 nanometers. Does the net transfer of kinetic energy and momentum between air molecules and nanoparticles in the fully atomistic model deviate from the hard sphere model? Can orbiting collisions increase kinetic energy transfer?
I think here what we have is the orbiting collisions are created. First of all, we preserve the energy, like make no mistake. Sometimes this term inelastic implies heat generation. Here with inelastic, we mean this essentially interaction of the force fields rather than the bang of the elastic collisions. It's more like maybe it's not the best term, but it has established in the literature. So what we really have here is collisions that they preserve the so-called all the kind of energy, and this is not affected. So I'm not sure if I answered your question, but maybe Naga, if you want to repeat it, because it was a bit longer.
Sure. You've shown that the probability of particle-gas collisions increases for nanoparticles smaller than 2 nanometers. Does the net transfer of kinetic energy and momentum between air molecules and nanoparticles in the fully atomistic model deviate from the hard sphere model? And can orbiting collisions increase kinetic energy transfer?
Okay, there is no change in the energy, either kinetic or theory or molecular, sorry, or Lennard-Jones, the energetics are identical. The only here is the events. And as I said, it is because of the, if I can use the word in terms of aerosols, the bigger effective diameter compared to what you have if you are using the classic sigmas, which are on the Hirschfelder book or the classic kinetic theory. If I didn't answer, maybe the colleague can pick up and we can discuss it lively. As we did it with Professor
Yes, for the last part of the question concerning if the air energy, the orbiting collisions increased. Okay, the general idea, as you amply mentioned, and you are absolutely correct, is that these simulations are carried out at total constant energy. So I mean, we in the statistical ensemble that we are operating so as to be so as to. I mean, there are known issues in the literature concerning that if you put a barostat to preserve pressure, air molecules are very sensitive. In some cases, we have also seen that. I mean, the impact of thermostat is much more gentle, but the impact of the barostat is significant. So what we did here, as you amply mentioned, is that we preserve the total energy. So I mean, you cannot. It's not correct to talk about heat generation. Okay. Now, orbiting collisions, I'm not sure if it is if they increase kinetic energy transfer, because probably we have slow-moving molecules. I mean, the reason that an orbiting collision occurs is because the relative kinetic energy between the both atoms or both gas molecules for the case of gas molecules themselves, or for the nanoparticle and the gas molecule, it means that the gas molecule does not have significant kinetic energy to escape from these attractive interactions. And if I remember correct, it's also mentioned by Hirschfelder et al., by Hirschfelder and Curtis and Bird, that these are not expected to have a significant direct impact.
Can I just jump in? I think you're sharing the screen still. Sotiris, your screen is being shared.
Yes.
And your emails at the moment.
Yeah.
Okay, just so you're aware.
Please send an email and I can send you either the presentation or the papers or whatever you need.
Yes. But definitely I wouldn't expect
but your email inbox is being shared on the screen. Is this on purpose?
I think you mean Professor Pratsinis, your screen is showing your emails as well. Just
Okay. So definitely I wouldn't expect an increase in the kinetic energy transfer from orbiting collisions. I mean, for sure I would expect.
Thank you. Any more questions? Wait, give a few minutes. If there are no further questions, we'll wrap up the session. Thank you all for attending today's lecture, and thank you, Dr. Pratsinis and Dr. Tselikis, for this fantastic work and a great talk. We enjoyed the talk a lot. Thank you.
Thank you, Naga. Thank you all.
Thank you so much. Bye.